So we're going to find out, does the temperature go up? Does the temperature go down? Is it exothermic? Is it endothermic? Oh, Mr. Gagnon, watch this one. Watch this one. And it's appropriate that we're doing this exactly 1 month before Halloween. Do you realize it's exactly 1 month before Halloween? It's the last month of September today. So the last day of September. So it says 26.6. That still seems kind of hot, but I guess it is hot. Okay, 26.6, well above room temperature. And I'm going to pour this amount in. And here we go. Let's see what the temperature changes to. Pouring it in. I made a little crater. To pour it into. This is a very good amount. I probably could have done it with a little bit less sulfuric. I don't even know if I'll be able to get it all in there. So what's it doing? Yeah, it looks like it's caramelizing. That's it. You know how they make brown sugar? How do they make it? Do you know how they make brown sugar? They melt some sugar, and then they use it to coat other sugar. So it's like sugar coated with melted sugar. It's like, what? Dude, is that necessary? So what's happening to the color? You guys are too far. What's happening to the color?
Turning black.
Does that look more like carbon?
Yeah.
So do you think that's all we're going to see? Watch. Oh, here we go. Hey, what's rising up out of this? What's this? Water. Now water, when it's moving and boiling, water can pick up bigger molecules, even as big as dextrose. Oh, okay, so I better back up. Is that a monster rising up out of a sugar bowl? Somebody's got to make a movie. Somebody's got to make that horror movie. Like the monster in the Crbohydrate, right? Okay, so now it's blowing toward me, so I'm shifting. Now, by the way, I just got a brunt of that, and it smells sickly sweet, like too sweet. And that's because, well, you might like it too sweet, I like it too salty. We each have our own. Please listen, guys, there's more to say about this. So, again, if it shifts towards you, just sort of, it's blowing all around. That's a pretty big monster. Now, what we've done is we've stripped off all those water molecules. Well, they weren't water molecules yet, but now they are. And when water molecules are moving rapidly, they can pick up things even like this big and carry them through the air, bounce them around. So you're actually getting sugar molecules carried through the air all the way to your nose. And there's a little bit of sulfur dioxide here, which is what the early Earth's atmosphere. This would have been like what the early Earth's atmosphere was. Now let's check the temperature now. I'm gonna stick it in. Hopefully I can get that back out. It's like Excalibur.
Yes, sir, it looks like a brownie that's burnt, like, to the max.
Right, because when you remove all the water from something edible, most of what's left is carbon. So that's why it looks so bright. Oh man, 123? So, I know, 120, I'm holding my breath. It's probably gonna like dissolve my mask. 128. Yeah, thanks. Good advice though, you're right. He's got an eye on that safety. What about you guys? How come nobody else was looking out for me? Okay, extra credit for Marlon, negative credit everybody else. We're not looking out. Okay, just kidding. So, it's 134. Okay, so I gotta remove that. I gotta remove that before it gets stuck, because what happens is, this carbon, how could it possibly come up to there when the sugar was way down here? Who has an idea? Can you see, can you see all those little holes on it? Maybe if I turn it. It's a little hot. Can you guys see all those holes?
Yeah.
So what happens is, the water is boiling, the carbon is left behind, the carbon is turned into a froth, like a foam, like when you're cooking, when you're washing dishes, a foam, and then it hardens. So this is like a very low density carbon kind of asteroid. Now later on, I might be able to, it's kind of hard to deal with it. Maybe at the very end of the lab, when you still have your gloves on, I'll have it so you can, when it's cooled down, I'll have it so you can handle it over a tray. Oh, that's a good idea. That'll be the last thing you do with your gloves though. So that we don't have to, because then you'll have to throw out the gloves. Okay, so what about, so that reached, what did we say, what was the temperature, 130? Well, at least we know whether it went up and down. I think it was, I thought the last one I had was 130 something. Did anybody get that? Okay, but the point is, you just have to know if it goes up or down. Okay, let's look at sucrose. Now, sucrose is another carbohydrate. Same thing, carbon, water. But look at this, wait a second. That doesn't look so pure white. Now, is that because it's sucrose? Well, actually, no. The dextrose should have looked like this. Also, did you guys realize that when we buy sugar, it is blanched? They do a treatment on it to make it look pure white. So why do they do that? Please listen. Okay. Please listen. I don't want to ruin the mess. Because back in the old days, before we had like Ziploc bags, before we had, have one. Where's my cup? Okay, here it is. So Ziploc bags are great because you can like seal things in, nothing gets in there. Back in the old days, they didn't have Ziploc bags. We used to have bell jars, which are these glass jars that you can seal tight. Before they had bell jars, people were always worried about if you leave your sugar in the pantry, what's going to happen? What? Think of something else.
Get hard?
What?
They get hard.
What?
When they get hard.
Hard? Okay, cake. That's true. I'm thinking of like something biological. What wants to eat the sugar? Ants. Everything wants to eat your sugar. So they would get bugs in their sugar, and you really wanted to be able to spot them. You'd have to pick them out, honestly. So it's kind of gross. So they said, you know what? Let's make our sugar pure white. Then it's so easy to see if it's clean or if anything's in it. So then they started blanching it, and then people got used to that. And now, if you try to sell sugar like this, they'll be like, wait a second. That doesn't look right. I'm going to buy this other one. So they know from a marketing standpoint, they keep blanching it for no good reason. For no good reason. Just because people buy that. It's kind of like how apples have to be a certain red. It's funny. So this is, to be legit, this is the real color of a carbohydrate. It's not pure white. It's kind of off-white. Yeah, but that's pure carbohydrate. It's before it's been processed. You have to process it to make it. Okay. So same thing. Now this has more carbon, but is that going to make a difference? Could be faster. Could be twice as big. Is it twice as much carbon? Could be twice as big. We'll see. And then I wasn't able to put in the full 45. I think I put in only about 30 though, which seems about right. Okay, so I'm going to pour. It says 28.9. Still seems kind of hot. But whatever. Let's just say, it's just dropped. Let's just say 28. Just remember 28. Let's pour in sulfuric acid, H2SO4. Oh, that's a joke. What is H2SO4? What is H2SO4? It's for dehydrating carbohydrates. Get it? Okay. So, and then while we're waiting for that to start, as you notice, sometimes reactions, even this reaction, that's a pretty good reaction, but it still took a little time to get started. So while we're doing that, we will see if I can write something on the French toast. I'm going to try to make a letter M because it already has those lines. Can I do it? I don't know why. I don't know what the M stands for. Somebody think of something good. And, oh wow, so when your mother tells you, Richard, please. When your mother tells you, don't eat that French toast, that's all sugar. That's all sugar. Is she right? Well, is she right?
Yes.
I just put a little bit on here to write an M. Look how quickly. This one is even, this is a different French toast than I usually use. It usually doesn't happen that fast. This one is all sugar. This one is. Okay. And then this reaction is still getting going. So while we're waiting for that to get going, I'm going to get the next one out. Just be patient. Remember, most chemical reactions are actually very, very slow. Think of rusting. That's combustion, by the way. Rusting is combustion. You know what? So it's like a very slow burn. Well, combustion doesn't have to be burned. There we go, there we go, there we go. This is a fun one, right? I mean, it's hard to impress. Some people it's hard to impress, and they stand twice as far as the house. You can't impress everybody, you know. Does it what?
Is it water because it breaks the bond between the hydrogen and the oxygen?
Yes.
Oh, it smells bad.
Yes, well then it's left with, it leaves behind the carbon. Yeah, the water would much, these like to be in a water molecule, very polar bond. Like oxygen can beat up on hydrogen a lot more than it can on carbon. If you really want to get into it, it's a polar bond. It's a much more polar bond. So it's just better off for everybody. So it releases all that energy. That's enough to boil the water. And to raise the thermometer, Oh, it's blowing my turkey. Nice. So did you guys, were you able to smell that smell?
Yeah, it smells horrible.
So imagine being in the early Earth's atmosphere before the stromatolites, like billions of years ago, let's say like 4 billion years ago, Earth's atmosphere would have smelled like that. And there was no oxygen. So that would have been a problem. Okay. So let's see what temperature this is before I get to the next. Oh wow. That one's a little harder to stick the thermometer in. Oh yeah. And then the last one, which I think is the funnest one, because I eat a lot of these spicy peas, sriracha peas, and the wasabi ones are so good. Okay. This is not sponsored by Happy. This is not sponsored by Happy Peas. Okay. So this one, what's the difference? This is another one of these, so why would I do that again? Because this is, what's the difference?
Oh, it's actual peanuts.
No. I'm just using the can. It's the right shaped can. It's powdered sugar. So that means that the grains are much, much smaller. So let's see if that affects the reaction. Like, does it happen slower, faster, more? Okay. And since this has so much in it, I'm just going to put a whole lot of sulfuric acid into this one. So this temperature is, wow, 146. And I'm just going to put, I think it was still going up. You guys are talking a little too much. It went up to 146. Do you remember what it started at?
126.
Like 26? Yeah. So that went up 120 degrees Celsius. And so now this one, let's get the temperature before. And I'm going to put a whole bunch of H2SO4. This is what H2SO is for. Get it? This one. This is my favorite one. So I hope you like it. Let's do the big one. I'm going to put in, I'm going to do 90 milliliters, guys. So let's see how this one comes out. Temperature before? What? How can that be right?
Still has the
Oh, it must have some, yeah, it must have some. It's way too high. You know what? There's no way. It's still dropping. So let's just assume it was about, what was the other one, 28? It's going to get to that. So let's just pour this in. Make a little pit. Let's have a monster on the 1 month, how would you say it? The 1 month eve of Halloween. Oh! It's not my birthday. Okay. Oh! What? Oh, I better move the carbon! Oh, no! Whoa! Oh, I gotta move. Pretty good, right? Okay, so that, did you notice? Did that happen slower or faster?
Oh, way
So think about, that's the effect of grain size. Just grain size. That was the same exact chemical as this one. Now this is too much of a mess to handle. I think I'm just gonna have to toss all this stuff. But these I will bring inside when they cool off. You know what I'll do? I'll put them on this pan